Welcome everybody to the presentation of our course, bachelor course in Mathematical and Computing Sciences for Artificial Intelligence. So this is a new program that we have established recently, and it has been the result of many discussions that we had at the international level with the colleagues, and in which we were trying to understand what is the most appropriate path that a student should follow in order to, say, become, to acquire all the tools that are necessary to create and to understand the AI, the current AI, and in particular the AI, the artificial intelligence of the future. And in order to do this, we need to discuss together what is actually artificial intelligence, what we mean by that, and probably you will discover that it's different from it's a bit different from what you've been imagining, and however, it is equally interesting, or hopefully even more interesting. Okay, so let me go to the presentation and share my screen and see if I can explain myself, and so that everything becomes clear. Okay, so we are discussing why we have established a new program called Mathematical and Computing Sciences for Artificial Intelligence. We are starting with a bachelor program because we believe that it's important that young students acquire the tools, and they should not specialize at the beginning. Before starting, let me just mention that AI is rapidly evolving, and so let me just mention the last two discoveries that have been done in the last few months, okay? Just to let you understand how, which is the kind of impact that this science is receiving from this tool. Now, one important discovery has been the capability of predicting the structure of proteins thanks to tools developed by DeepMind, who is a company that is doing research in machine learning and artificial intelligence. So the problem they have solved is the problem of going from the sequence of a protein. You know that the proteins are the bricks of life, right, in the cells, and proteins are like a necklace with a lot of amino acids, right? And from the sequence of the protein, one would like to predict the structure of the protein, because the structure encodes for its functionality and so for its role in the cells and so on. And this has been an open problem for 50 years. Huge groups with a lot of computer resources and so on have been trying to understand how to go from the sequence to the structure. And just in the last months, this result was achieved thanks to a machine learning technique and artificial intelligence technique. So this company was able to increase, say, the score from, say, 40–50%, which is interesting but not particularly relevant for experimental validation, to close to 90%. And so this is a huge jump, which means that essentially now we are able in vitro to predict the structure of a protein, and this will allow us to design, say, new drugs and to understand a lot of things about the role of proteins in cells. Okay, so this is a huge, you see, in a couple of years, we had an enormous jump in performance, and so this problem, at least the problem of the structure prediction, has been partially solved all of a sudden thanks to these new tools that I will explain shortly. Another, big improvement that we have observed in the last months has been the capability of creating text. So the improvement in natural language processing. There is a new network called GPT-3, which is a new artificial intelligence system developed by OpenAI, which is another company doing research in this field, who is actually able to, who has learned words from all the text found on the web, and now is capable of actually writing and doing a lot of manipulation of languages with an incredible accuracy. This is a snapshot of an article that has been written by this machine. And if you read it, it's kind of surprising. It's almost scary because it looks really written by a human being. Now, the secret is that behind this text, there are some sentences that are used by the machine as an input for creating the text. So the logic, the rationale is actually given by a human being. However, the network is capable of writing a very coherent text using the input. So it's not intelligent, but it's incredibly efficient. Okay, and the machine that has done this, which is composed of an enormous number of parameters that need to be tuned. So it's a very complex system, and I will describe it to you later on. And the number of parameters of the order of 180 billion parameters, so something which is absolutely enormous. So what is our course about? So in order to understand the kind of discoveries that I just told you about, but these are just a couple of examples. There are similar things happening, and there will be similar things happening, in economics, in physics, of course, in biology, and in many fields. We will see. Now, in order to understand these complex tools, and we need what do we need to know? Well, we need to know the fundamentals. We need to know computer science in the sense of the theory of algorithms, programming, and so on. But we need to know mathematics, because this is the common language of all the hard disciplines, hard science disciplines. We need to know modeling techniques, those that come from physics, those that come from economics, because as we will see, AI is concerns a lot modeling systems, right? And then we need to know some specific topics related to AI. So the theory of learning, the theory of intelligent systems, and part of neuroscience, and so on. So our program plans to put together all these tools in a very coherent way. So we are asking you a lot. We are asking you to learn a lot of things, but as a result of this learning process, you will acquire a lot of freedom. The freedom of being able to choose your future, in the sense that once you have all these tools, you can actually choose, let's say at the master level, the kind of specialization you prefer. Okay, so what our program aims at is to give you all the tools that are related to this topic, which are fundamental for AI, but can also be fundamental for all the other quantitative disciplines. Okay, so let's start to understand what AI is. Which is the kind of AI we are talking about? So can machine think in the traditional sense? The answer is no. Okay, so you have to imagine that all the machines we are talking about are not actually capable of any human-like behavior. Okay, and I should say that no progress has been made in the last 50 years, deep real progress in this direction. So thinking machines in the sense of Turing, so in the say human-like sense, are logically infinite distant. So the kind of AI we are talking about today is not the AI that you might have seen in some science fiction movie. So current AI is concerned not with intelligent machines, but it's a tool to augment our cognitive capability. So it's a tool, a new tool that we have, a very powerful tool to analyze data, to model data, and this can, lead to incredible outcomes, because we have really new capabilities for understanding problems, and so this, opens a lot of doors in all directions. So we're going to discuss briefly how it works and what it means to have some superhuman performance in specific fields. And I think it's also important to understand when all this happens, so that you can realize that you're just living in the right moment. Okay, so what I would like to clarify is that, before even thinking of creating a machine that thinks like a human, what we need to do is to have a machine which is capable of taking the data from some inputs, from some external world, okay, or external stimuli, and then it's capable of extracting information from this data to create internal representation of the data, and that can continuously learn from the data. Once we have this kind of machine, we can, on top of this, hope to create some kind of intelligent behavior. But so whatever we are talking about today concerns this kind of capabilities. So the capability of extracting information from data, not about the capability of thinking about data, right? So this is something that is left, say, to us. Now, the capability of quickly analyzing data, getting new features from the data or whatever is easy for humans. When you look at a natural scene, you immediately spot if there's something wrong going on. But it has always been very difficult for computers. So computers were not very good at generating text, sounds, or images, right? Or I mean, generating or recognizing. But all of a sudden, in the last year, this has become possible. Okay. So the kind of artificial intelligence we are talking about is in fact called machine learning. And it has to do with the capability of extracting information from data and build new models, theories, solutions, application out of that. And there are a lot of branches of machine learning, but the one that has influenced research and application mostly in the last few years has been deep learning, which is the machine learning implemented by artificial neural networks, which are systems that somehow remind us of the human visual system in a very superficial sense, but these are layered structure that extract information layer by layer. And these are just one example of the tools using machine learning, but their performance has really opened new paradigms in the way we do science, in the way we do application across, say, fields, technology, business, biology, society, and so on. Now, in order to understand this, let's try to understand what, say, traditional artificial intelligence is supposed to be. I mean, this is just a very, very simple example. Suppose we want to say, in a traditional sense, we want to write a code or a program that recognizes an object in an image. So let's say we want to recognize a chair. Then the kind of things we have to do is to write in some computer language a code that is saying something like this. The object is a chair if it has 4 legs, it has a flat surface to sit on, and it has a backrest. Okay? Then if these conditions are satisfied, then the object can be considered to be a chair, right? And this perfectly works for the first chair in the picture. But however, it doesn't work for the second one. Now, so you see, because it doesn't have 4 legs, but it has 5 wheels. So what are we supposed to do? Well, we are supposed to do to go back and modify condition 1 of our code and say if it has 4 legs or 5 wheels, then, and all the other conditions are met, then it is a chair. But again, this would solve the problem for the first 2 examples, but it would not solve the problem for the third example, which is a chair with curly legs. So what we should do is to go back once more and modify the code again and write, well, it has, if the object has 4 legs or 5 wheels or curly legs, then if all the other conditions are satisfied, then it is a chair. But you see that this is a never-ending story. We will never be able to write a code that a priori can predict all the condition. What would you write for this kind of chair, for instance? Okay? But on the other hand, we know that it must be possible because we immediately recognize, it's very easy to recognize a chair, and also for a cat or for another animal, a dog, whatever, it's very easy to recognize a chair, where you can sit and rest. Okay? So the idea is that we cannot use this traditional approach, right? We need another approach. Instead of coding, we need to learn. We need to learn from examples. And this is actually what modern AI is concerned, learning from examples. Okay? And so, for instance, there's this very famous challenge of discriminating between cats and dogs, and this can be done using some traditional method, and it turns out to be very, very difficult. However, if you do it by learning from examples, it turns out to be solvable. Okay? So machine learning is about learning. And learning can be performed in different ways. There are different types of learning, so-called supervised learning, in which we have data that have been pre-processed by humans with all the labels characterizing the content of the data, and we use this as a training set for our artificial intelligence system. Then there is unsupervised learning, in which the system has to learn just from raw data that have not been supervised by human. Or there is another type of learning which is called reinforcement, in which a system which is controlled by some artificial intelligence network learns from its mistakes, okay? And it learns to behave in a certain environment. So these are just few examples of all the set of tools of machine learning, okay? And again, let me stress that in order to understand this, you need to know computer science, math, and modeling techniques. So let me just briefly tell you what are deep networks. Deep networks are the tools of machine learning that have really revolutionized the situation, say, in the last few years. Now, these are systems that are very similar, are just a stylized version of a neural network. So let me just tell you how they look like. So you have to imagine that these are systems formed by many layers. You see there's an input layer, first layer, second layer, third layer, and so on. So there are many layers. The data, the input are injected from the left, and then you read the results of the manipulation of all this information on the output layer on the right. Okay, and each node implements a nonlinear activation function. So which in very simple terms goes as follows: if the sum of all the inputs that are arriving to the node is above a certain threshold, then the node itself is going to emit a signal downwards or to the right, say, that is going to influence to reach all the neurons in the subsequent layer. Okay, so you have to imagine that you start by activating this node with some input. Imagine pictures where each node here would correspond to a pixel in a picture, and then so this node here is sending information, sending a signal to all the nodes here, which are called neurons, but they don't really have to. They are not really neurons, they're just formal neurons, artificial neurons. And so these neurons receive the signals from the previous layers, and if the total signal, incoming signal, is beyond a certain threshold, then in turn they emit a signal so that the information is propagated from the left to the right. So this is a very complicated object that implements a very high-dimensional nonlinear function. Okay, so you have to imagine that what I've drawn here in these slides is just a little example. Real networks can have a number of links, these links here, that connect the different neurons, which is of the order of millions or billions. So they're really huge systems that require a lot of computational power. The key point here is the following. These nodes here are somehow fixed. They just react to the incoming signal and they emit the signal in output. However, the links themselves can have different weights, which means that you can imagine each link as a tube in which some water can flow. And the idea is that if you have a large diameter, a lot of water can flow, and if you have a small diameter, a little amount of water per unit of time can flow. So you should imagine that each link can have a large weight or a small weight, and this weight will determine how much a certain node influence the other node. So you see, in this system, you have a number of parameters which is equal to the number of weights, so equal to the number of links. So each link carries a real number, and these are the parameters that we have to identify in order to train this system to behave as we want. Now, as we will see, the first layer or the first layers of this kind of networks specialize in understanding how to decompose the input in fundamental features, which can then be used by the last layers to perform the classification. So you see, they have a first part which essentially is capable of figuring out what is relevant in the input, which can be very, very complex. And then the last layer are used for associating this decomposition to some classification purpose. Okay, so this is how a real network looks like. So you have to imagine that each block here is of this type here with a lot of parameters. So these are really very, very complicated objects. So how does learning take place? Learning takes place in the following manner. Suppose that we want to use this network to recognize, for instance, say the presence of a chair, a table, a lamp, or whatever in a certain image. Then what you're going to do is the following. You present in the input, you start with random weights on the links, you present on the left your image, and then you look at what the output tells you. Let's say that, the first node in the output here encodes for the fact that in the input there is a chair, the second one for the table, the third one for the lamp, and so on. Okay, so let's say that you have decided this, and you present a picture of a chair, and you find that the first node in output lights up, so it becomes active. Well, in that case, everything is fine. The network has classified the input as a chair. However, if let's say another node lights up, activates, which it does not correspond to the correct classification, which you know because your data are labeled, you know that you're presenting a picture of a chair, so you know that the labeled chair in output should, the unit chair should light up. Then what you do is you propagate backward an error signal, and you actually modify all the weights a little bit in order to increment the activation of the correct output. Okay, so you repetitively show some input-output example, the so-called training set. If the network does not give the correct outputs, all the millions or billions of connections are automatically adjusted and modified in order to activate the correct output unit. And then this step is repeated millions of times over many, many examples. Let's say over a million of examples. Once the network has learned to classify correctly all the examples, we can stop and use this object for what? For making predictions, because how you can use it as follows. You present in input an image that the network has never seen, and you just read the output. And this will tell you how the network classifies this new input. And this can be a prediction. In which sense? In the sense that if you have shown to the network, if you have trained your network to classify correctly a rich training set with a lot of examples, let's say, of chairs, then the network will be able to actually classify it correctly as a chair example that it has never seen. So it becomes capable of generalizing. Okay, so this is the trick. You learn from example and which are the critical features that characterize the object chair. And you don't have to tell them a priori. It's something that the network learns by itself. Okay, and this is very important. If you imagine that instead of just a picture of a chair in input, you give, I don't know, some DNA sequence or some financial data or whatever, the network is going to be able to tell you what is relevant in the input in order to perform certain type of classifications. Okay, so this is essentially the idea. So the novelty of modern artificial intelligence is that we have moved from a traditional approach in which we, human, a priori define which are the important features in order to perform certain classification. Let's say in the case of dogs and cats, we might want to say, well, if there are some triangular features, then this should be a cat, otherwise it should be a dog. Well, this approach in which we, human, define a priori which are the important features doesn't work. It's never worked really well. However, with the modern approach, we are going to learn not only to classify, but also from the example, we are also training the first layer of the network that are going to tell us which are the features that are relevant for the classification purposes. And these are geometrical features that you can figure out by looking at how the various neurons in these layers are activated. But this is a technical point that you will learn later on in your life. Okay, but the key point is that now we can do end-to-end learning. So not only we learn to classify, but we also learn to understand the input. So when has all this really happened and started? And why are we talking about this today? Well, it has started, let's see, if you want to keep in mind a date, in 2012. Okay, so just right 8 years ago. So at that time, there was say, a competition between all the scientists working on vision. And the competition consisted in trying to figure out the presence of one among 1,000 different objects in a given image. So there was a set of images, and this set is called ImageNet. These are images downloaded from the web. And all these images can contain many different objects inside. And the task consists in writing a code which is capable of detecting the presence of one among 1,000 different possibilities. Okay, so it's a very complicated task. It's not just chair or not chair. It's really, chair, table, lamp, phone, and so on, 1,000, and so on, 1,000 different objects. Now, in 2011, the performance of the classification error over the training set, over the test set of this competition was about 26%, which is quite bad. You have to keep in mind that the human performance is 5% of error if you try it. And that in 2012, the research group of Hinton in Canada trained a deep network, an artificial neural network, to perform this task. At that time, it took a lot of time to train over all the examples of this network, but all of a sudden, the performance dropped down from 26 to 16% of error. So it was a 10% improvement. And this was, had a huge impact because nobody predicted this. And since then, this artificial neural network, this network have been improved. And nowadays, they can detect the presence of objects with an error that is around 2%, which is well below human performance. So it means that these kind of tools for this specific topic, objective, are actually superhuman in their performance. Okay? And so this is the kind of output that this kind of network gives you. So you present an image like this on the left, say, and first of all, the network is capable of bounding the objects inside boxes, and then it's capable of telling you what's inside the different boxes. Okay, so for instance, the network for this picture here is going to tell you, well, that this thing here on the left is a car with a probability which is 1. It's certain that it's a car. Here you have a person with probability 97%, 98% almost, and so on and so forth. So this is the kind of how the output of the network reads. So the unit corresponding to cars is going to be totally active for this. In this example, the unit corresponding to a person for this piece of image is going to be almost totally active. The activity of the output is between 0 and 1, so it can be interpreted as a probability. In the case of the discrimination between, say, dogs and cats, you see that in this case, again, the network is going to bound the animals inside boxes and tell you that this is a cat with probability 98% and this is a dog with probability 99.4% and so on. So this is really the kind of output. So these are impressive and incredible performance that have appeared just in the last years. And this is why we are talking about self-driving cars, right? Because now self-driving cars are capable of recognizing the presence of objects with great accuracy is, on the streets, for instance. And however, and so the visual system of cars is extremely powerful. It's better than our system because they have a lot of cameras and a lot of tools, and however, you still don't see cars around, self-driving cars around. Why? Well, because it's true that they can recognize whatever is on the street, but it's also true that taking decision requires a higher level of intelligence, which is not what we are talking about today. So this might become true in the near future, but I think that we will not, immediately see this kind of, say, cars, for instance, around, at least in a generic, in an arbitrary street, maybe in some very controlled situation, or yes, but not, but it's hard to imagine how to see this object, these cars around in uncontrolled situations. But the key point I want to make is, that it has become possible to essentially read images and understand what's inside. And this has a lot of applications. For instance, in medicine, you can use this to recognize the presence of anomalies when you want to do in mammograms, if you want to predict if you want to do the screening for breast cancer, and so on and so forth. So there are a lot of application across fields, and I leave to your imagination, all the things that you can do with this kind of tools. Now, why do we discuss about AI today and not 10 years ago? Well, the reason is that 10 years ago, we did not have these tools, right? And things just happened in the last decade, because in the last decade, first of all, we had at our disposal a lot of computer power, thanks to the availability of GPUs. So these are the kind of processors that are used for gaming, computer gaming, which can be used to actually perform all the training process that I described to you. And so all of a sudden, in the last decade, scientists that have been had the possibility of having on their desks for a few dollars, literally, say $1,000, extremely powerful tools that which are more powerful than the fastest computer existing, say, just 20 years ago. So this has led to the possibility of having a distributed research. So a lot of labs have made experiments and started to work on this, and so a lot of progress has been made. And then, of course, there is the issue of data. Data with the web, a lot of data has become available. Not only with the web, also the technological machineries that are used, say, in science, medicine, and so on, are producing a lot of data. So now we have the computer power, the data for training purposes, and also novel algorithms have been developed. And just to give you an idea, Facebook, Instagram, and WhatsApp, which actually belong to the same company, which is Facebook, each day they upload and these images are used to train this kind of neural networks. Okay, and so you see that things, these technologies will become even more pervasive. So we need to be prepared. We need to learn how to use them and to develop all the most appropriate tools to control everything. So this is just a summary of some achievements obtained in the last decade. So around 2010, there were the first experiments about speech recognition, but the breakthrough really came in 2012 with the ImageNet competition that I told you. And then in 2013, there were the first application in personalized medicine. And then at that point, a lot of industries started to raise their interest. And in particular, the tech giants started to invest in these fields. And then since then, a lot of applications have been developed. And I mentioned to you at the beginning 2 recent discoveries, but protein folding and text generation. But there are many applications. So let me just go through a few of them. Okay, so I mean, what this kind of machine can do today, for instance, is take an image, from this image extract the content, so recognize all what's inside the image, and then using a language generator, so a natural language processing device, you can actually write a text which describes what's in the image. So again, this is not intelligent behavior. This is just translating an image to text, okay? But it's extremely useful, and you can imagine how important it is, for instance, of course, not only for visually impaired people, but in general, to communicate information. Now, something that also you might have heard about is the fact that these kind of tools have been able to win at games learn strategies for playing games. And this is very important, not because of games, but because of the impact that this may have in science, technology, business, and so on and so forth. So in particular, I'm sure you've heard about the game of Go. The game of Go is a very complicated game, which is simply stated but complicated to play. So it's a 19 by 19 grid, and you have black and white stones. You have perfect information in the sense that you see, what's on the table. And once you place a stone, you cannot move it. So you can only capture the stones of your opponent by surrounding its stones with stones of your color. Okay, so let's say that this stone here is captured by black stones. Okay, and the objective is to control at least 50% of the board. At that point, you win. Now, this game is very complicated to play because each time you have to decide where to place your stone, you have an enormous number of alternatives. And so if you imagine to iterate this game, the space of possible strategies grows exponentially, and it's really impossible to imagine to explore in an exhaustive manner the alternative moves. As it has been done for chess, chess is very different in this respect. It has a much smaller space of strategies. And so this was considered to be a game out of reach for computers. And this is what happened, is that a company called DeepMind set up a system in which it trained artificial neural network to play one against the other. Okay? And so to learn by repeated games. And by doing this, this network could play a number of games in few hours, which is, of course, much bigger than the total number of games played by humans in whole the history of this game, which is very old, it's 2,000 years old. And so the idea is that by repeated games, this network can select the best strategies for playing this game. By construction, this network cannot explore all the moves because, as I mentioned to you, it's just the space is too vast. However, by playing repeated games, they can, explore the set of strategies rather than the set of moves. Okay, and this has turned out to be very successful. So a few years ago, the European champion was beaten by Alphago, this program. It's called Alphago, and then the famous game with the Lee Sedol, who was the world champion on Go, was performed in 2016, and since then, the game is over in the sense that this kind of system, outperform humans. Now, what I would like to mention is that the very same company, or my research environment that has built this device for playing games, this is a scientific result, it was published in one of the most important journals of science, is the same team that has, not the same person, but it's the same institution that has also solved the protein folding problem this year. So you see that you create tools which can use with appropriate integration of information in totally different contexts. And so you see, you start from an application which sounds like a bit useless, like playing a game like this, and you reach immediately a fundamental result in science, for which I expect probably a Nobel Prize in the next years. Now, so this kind of learning is called reinforcement learning, which this network play a lot of games and they learn from their mistakes. Unfortunately, this kind of learning cannot be used to train cars to drive, because you cannot repeat millions of times an accident. And so there are limitations. So this kind of learning can be used if you can simulate the environment in which the application can be used, okay? And but this does not solve all problems. So this is an example of reinforcement learning, which can be very successful in many applications where you can simulate your system so that you can repeat your games many times, or your prediction many times, or you can detect which is the effect of your action and correct based on this, but only if you can make simulation. In reality, this is not the kind of approach you can use, because you cannot repeat a mistake a lot of times. You cannot destroy a car. This car is actually going out, it's not turning properly, and millions of times, right? So there are some limitations. This is why I told you that there are different forms of learning. Now, let me give you another example, which is pretty interesting, I think, and gives you an idea of how flexible and powerful can these kind of tools be. So let's assume that we have trained a network to discriminate, not only to recognize an object in an image, but just to tell you a simpler thing, just if an image is real or if it is fake. Where by fake, I mean generated by some computer, by some Photoshop or whatever technique you want to use to generate a fake image. So you create this discriminator, which is called D here. And we know already that this network can be very, very efficient in doing this, because the performance are actually superhuman. And so you can create this discriminator, and that's fine. So you have an object that you plug in an image, and then it's going to tell you, well, this is a true image, or no, this is a fake image. However, at this point, we can create another network that takes as an input a blurred image or even some random noise, doesn't matter, and it creates an image which, and this network has the scope to create an image that is going to fool the discriminator. So it wants to create images that are recognized as real by the discriminator, even though they are artificially created. So now you have these two networks. Somehow you can train this generator network many, many times. At the beginning, you make a lot of mistakes, but you're going to correct all the weights in this network until it's able to create images which are recognized as true by the discriminator. Once this is done, you have an object which is capable of creating realistic images from partial information. Okay, so let's say that once you've done this, and this has been done, and these are called generative adversarial networks, because this is a generative object that generates images, adversarial, because images against the discriminator, right? So that it can fool the discriminator. And clearly, if it succeeds, it means that this network has learned to generate images that capture all the statistics of natural images. So once this is done, you can feed the generator network with an image like this, in which you just delete a lot of pixels. And then the network has never seen this image, so it's not recognizing the image. It's just going to fill the missing information so that the picture is going to look realistic. And this is the result. You see, it's quite impressive. Or let's say you give this input to the generative network, and then it completes the image like this, and this woman does not exist. Okay? Or you give this image here, and this young man does not exist either, even though it looks quite real. Okay? And so in order to let you understand what's going on, is that let's assume you remove some object from an image. So now you have this image, and you have a person behind the bars here, and you just delete this information, and you provide this to the network. Clearly, the generative network cannot know what's behind the bars, because the information is missing. So it's going to complete the image in such a way that it looks real, even though it's not, but it cannot construct the information that it doesn't have. And in fact, this is what is created by the network. So it's a realistic image, just without, so you can delete objects in a very realistic way. So this is an example of application. You can use a bad camera on the left to take a picture. So let's say you have a very cheap camera with very, very low resolution, and then you obtain a certain image. Then you provide this image to the generative network as an input, and the network outputs an image that has a much, much higher resolution. So actually a beautiful image. I mean, if you look at some details, you might recognize that there are some pixels that are, not totally reasonable, but in fact, there's no doubt that on the right here you have a picture that has it's kind of much better than the one you have on the left. And all the pixels that have been inserted here in order to increase the resolution satisfy the statistics of natural images and are recognized as real by a discriminator. So this, of course, has application in medicine, imaging for medical applications, because you can increase the resolution of a lot of type of images. Okay, fine. So I just gave you a few examples of this kind of research and tools. Now there are many, many things that need to be solved for the future, like using this machinery, these tools to understand causal relationship between events in a stream of data, for instance. One has to improve algorithm to perform better learning, and to close the gap with with human intelligence, or at least with the human pre-processing of information. I don't want to talk about intelligence, because as I'm trying to explain to you, we are not talking about that. We are talking about extracting information from the data. There's no doubt about the fact that this optimization-based data analysis will continue to grow, and all these network technologies and these models will be present, and they are used across all the disciplines. So it's extremely important to master them. Okay, so it's very difficult to predict which will be the next big discovery that is going to happen in this field, or the next big application. For instance, nobody could predict the results about protein folding 2 months ago. It was kept secret in the research lab and just published recently, but it's so it's very difficult to predict any specific huge jump. But what is kind of sure is that all these tools that are used in all disciplines, from molecular biology to astrophysics to business and to social sciences, will help to boost the rate at which discoveries are obtained, at 360 degrees, right? With application that can be almost immediate. Okay, so as I mentioned, these are used, in gene editing. You use machine learning to reduce collateral effects, in cell programming, in analyzing climate change, in economics modeling, in astrophysics, in medicine, neuroscience, in all the. And I want to mention that machine learning itself is a field of research. We just started to understand the behavior of these systems. Okay, so the idea is that in the last say 50 years, computer scientists engineers have programmed, have written a lot of line of codes, programming algorithms and so on. But now we are in the phase in which we are training machine, which is different. Okay, and this requires domain knowledge. It requires a lot of math and modeling tools in order to understand how this complex system actually behaves at the end. These are not simple programs. These are very complicated objects which evolve under training. Okay, and there are many fundamental questions associated, and depending whether you want to understand them or want to do application, but you might want to have a deeper understanding of their functioning. But you need to understand how they're working. Okay, now we are very far from still very far from how we learn, from how a baby learns. For instance, in a very superficial sense, let me just summarize the state of the art as follows. Babies learn by continuously making predictions about the environment and checking if their predictions are correct or not. And this is not for the moment how neural networks are trained, even though there is a research in this direction called self-supervised learning, but I don't have time to discuss about this. But let me just mention that if you show a flying car or a flying toy to a boy which is, say, 7 months old, for him it's totally normal. He's not going to react. Why? Because it's only at the age of 8 months that the baby develops the idea that there is the force of gravity. And therefore that objects are supposed to fall down. I mean, he doesn't think about force of gravity. Just in his model of the world, he understands that objects are supposed to fall down. And so if you show the same picture to a 9-month-old baby, then he's going to be very surprised by the fact that this little toy car is flying. Okay? So this idea of making continuous predictions about the environment and based on the outcome, on the matching between our prediction and the environment, learning from that is something which is understudy and will be understudied in the future, but we are still very far from that. Okay. Now, in order to understand, I hope I have kind of explained to you that I've given you a few examples, but the key point is that if you want to understand how this very complicated nonlinear object, evolve and how generalization capability emerge from this object and how can be improved, designed, applied, and so on, you need to know math, you need to know computer science, you need to know how to model systems, and you need to know machine learning. And so everything in a coherent work, and this is what we are going to provide in our course. Okay, so the idea is that we have set up this mathematics and computing science for artificial intelligence course, in which really the objective is to give you tools. First of all, to give you all the tools which are necessary in order to become to master this kind of new knowledge that is emerging from AI. Okay, so we need to give you something that is not going to become, say, old in a few years. We want to give you the fundamentals that will be valid 10 years, 20 years from now, or even more, so that you will be able to capture all the novelties and all the new results that emerge, or you yourself will be able to do them, right? So this is the idea. And so for these reasons, we're going to teach in parallel the math, the computer science, the physics, and the economics, which are necessary in order to model complex systems. And therefore, putting all these things together, you will have the background which is necessary to understand, the AI tools in the sense of machine learning that I was talking about. So in this program, you will learn a lot of math, a lot of computer science, physics, economics, and of course, there are other courses more specific in machine learning. So let me, so why, in my opinion, in our opinion, and I should say in the opinion of a lot of colleagues around the world, this is a very important and, say, useful program for young students. First of all, it is a program that it is at the intersections of all the knowledge, different backgrounds that are needed to understand and develop AI tools. You will learn different point of views with respect to modeling and computing issues, and therefore you will have a critical thinking based on some deep knowledge, which is going to really prepare you for the future. Let me say digital era, which is almost obvious. We are not going back. The new era will be digital, but of course, will be dominated by data. And the idea is that we need to develop all the tools that are necessary to manipulate the data, to understand, to extract information from data, and to put all this information together what we already know about the specific domain we are interested in. So I'm not saying that these tools are going to replace the fundamental knowledge. I'm just saying it's a new tool that has to, put to the full benefit, say, of the domain knowledge information. Okay, so which can be whatever field of science and technology you are interested in. Okay, and the kind of knowledge we're going to provide you is going to remain valid in the future as new technology emerge. So we are focusing on fundamentals. Okay, and so what is the study path? Well, the study path is, well, of course, you have a lot of compulsory course, and then you have IT skills, foreign language and soft skills, and so on. And of course, as for all Bocconi courses, you will have the possibility of having exchange programs, internships, which are very important. But what I really want to mention is that you have a lot of compulsory courses and some few elective courses that will allow you to, during third year, to actually choose maybe to make a step towards what will be your choice for your future. So you can choose the elective courses depending on which kind of field you want to specialize at the master level or in your job. Okay, so let me just show you how we actually perform this parallelization between different, implement this parallel approach to learning. Okay, so the idea is that in the first year, you first of all well, you start with the course in Foundation of Economic Science, and this is intended to be a course in which you learn how to model social systems. It's about modeling. You will have a fundamental course in computer science, and you will learn how to program, and then you will have a mathematical analysis module and an algebra and geometry module. These are kind of fundamentals that you need to know, because as you will discover, all these tools, computer science, mathematical analysis, and algebra and geometry, are all fundamental in building AI systems. Then you have, in the second semester, a foundation of physics, which is again a course about how to use math for modeling. And then you have a computer science course, which is about the theory of computing. Then you have a probability and mathematical analysis. So this first year, you see, it's very, very tough, and it's about fundamentals. Okay. During the second years, we continue. You have a foundation of physics 2, in which you learn how to use different type of math for different type of modeling, different type of physical laws. Then you have decision theory and human behavior. Again, this is about modeling decision theory, which is important for also for AI and economics. Then you have mathematical statistics, which is one of the basic tools for data analysis. And then we have advanced analysis and optimization module 1. Then you have an advanced programming, in which you learn how to perform optimization, which is, as we learn, a key step for machine learning. And then you will have the first real course in mathematical modeling in machine learning. Okay, and then you will have a first AI lab, in which you can apply what you learn in this course here to some concrete data. And then you will have some, for instance, digital ethics seminars and foreign language and other important programs. Then in the third year, you will learn about statistics and quantum physics, because this is the highest level of modeling you can think of in the physical world. Then you have game theory and mechanism design, which is again a very high level way of describing interaction also in social systems. Then you have mathematical modeling applied, for instance, to finance, which is again a context in which you might want to apply also tools coming from AI. And then you have a very important course in stochastic processing simulation in natural science, which means that you learn how to simulate systems, because simulating properly can be helpful for learning, as I mentioned to you in the case of reinforcement learning, for instance. And then you have machine learning and artificial intelligence. This is an advanced course in machine learning. And then you have a course in mathematical modeling for neuroscience, which puts builds the ground for linking machine learning and neuroscience. And then you have elective courses and internship, and the elective course is also important. There is a course in information theory, there's a course in math, and then there are all the courses that are provided by Bocconi in case you choose to focus on some application, let's say in finance, in economics, in management, in marketing, whatever field you might be interested in. But what I want to say is that when you have completed this course, you will have the possibility of choosing whatever future you want, in the sense that you might want to choose to continue towards an academic path or a research path in machine learning, or in math, or in physics, because as you see, or in computer science even more, because you see that you have learned all the fundamentals. Or you might want to choose a more applied field and apply all these tools that you have accumulated in specific application. Okay. And the career opportunity, of course, are enormous. There's a big need for brilliant young people that have a strong modeling and a methodological background, because quite often you need to model problems in this very complicated, say, world, and then use the appropriate tools. Okay, so there are a lot of possibility of applying this knowledge in already at a professional level, in some working in companies, but you can also imagine to continue your studies at a graduate level, focusing on different type of paths, like it could be artificial intelligence, it could be applied math, data science, computer science, physics, economics, finance, business, and so on. okay, or even computational biology. I hope it's clear that we are providing the fundamentals for modern science. Now, also, the job market is also open directly. I mean, I know for sure that by experience that a lot of companies are searching for young people that are trained in this modern way and are not just specialized, but have really a very strong background. Okay, I hope that I was able to communicate what I think is the main novelty of this last decade in science. That is that we have a new tool which is very general and can be applied to different fields. It requires a lot of knowledge in order to be understood. It's an interdisciplinary background which is needed, and we are going to provide this. And again, it's a very tough path, but it's going to give you the freedom of choosing your future once you have learned this. It's like going or reaching the top of a mountain. Once you have reached the top, you can, very easily go down where you want. And I think you will never regret learning the fundamentals and in this modern context, because you will be an active actor of the new discoveries and the new applications that will emerge in the near future. Okay, thank you.